Hello everyone, welcome to my video on elementary differential equations. This is video number 11 for chapter 3. In this video, we'll focus our attention on the reduction of order. So this method can be used to find a second solution, let's call it y2, if the first solution y1 is given for a second order linear equation, and the equation does not necessarily have to have constant coefficient. So we see that it's a more general method, covers a type of more general second order equations that we have been studying so far. Okay, so far all the equations we have studied are homogeneous with 0 on the right hand side. Let's get into the subject through an example, and hopefully the method becomes clear along the way. Okay, let's consider this example. So we have the equation 2t squared y double prime plus 3t y prime minus y is 0. And it's defined for t bigger than 0. And the reason for this restriction is that this equation can also be written in this standard form where our existence and uniqueness theorem applies, where the coefficient in front of y double prime is 1. Therefore, you can divide both sides, or each term here, by 2t squared, and I get y double prime with 1 in front, and then I get 3t over 2t squared, cancels the t, I get 3 over 2t, and then here I will get negative 1 over 2t squared y equals 0. And then you see that for this equation, we don't know the existence of solution where the denominator here becomes 0. So it has to be on only half of the real line at t bigger than 0. Okay, so for this equation, we are now given a solution. So let's say, provided that y1 equals 1 over t is a solution, and then the job now is to find a second solution, linearly independent, and let's call it y2. So the method reduction of order can take various forms in different settings. So we'll go through this example, this equation here, with this y1 given, and we will present 3 different methods to find the y2. And then we will do a summary. Method 1. Here we propose to use Abel's theorem and to use the Wronskian. By Abel's theorem, and we can set the constant c equal 1 in the theorem, then we have the Wronskian of the two solution equals exponential of negative of integral of pt. So here the p is 3 over 2t. So we are very familiar with this type of integration, and dot dot dot, a little bit detail you can work out, and you will get t to the negative 3 over 2. Now let's use the definition of the Wronskian. And definition of Wronskian says this Wronskian is y1 y2 prime minus y1 prime y2. And now y1 is already given, is 1 over t, we put it in. And then y1 prime can be computed negative 1 over t squared, and we put that in. So this is another formula for the same thing, the Wronskian. And then they must equal each other, and therefore we have this equal to t to the power negative 3 over 2, and we see that this now is an equation for y2. And we see this is a first order linear equation from a glance, right? And we know how to solve that. Okay, we can simplify this by multiply with t on both sides. Then we get y2 prime plus minus is plus 1 over t. y2 equal, here becomes t to the power negative half. Okay, this is just a first order linear equation. We have our standard method of integrating factor. So I'll be brief here. So compute the integrating factor. We get mu is t, and then use the formula for y2 is 1 over mu integral of mu times the g, the right hand side, and you work out the integral and you get 3 over 2 square root of t. Okay, a little bit detail here you can fill in. Okay, so the constant here 3 over 2 and doesn't really matter, because if y2 is a solution, then since this is a linear equation, multiply y2 by any number is another solution. So we can just drop this constant and take the simplest form for y2, which is square root of t. So here, if you don't do this step and say y2 equals simply equal to that, it's also correct. Okay, so we see that this method works, and we see that in this method we used the powerful Abel theorem, and we utilized this definition of Wronskian. And now let's introduce method number 2. So in this method, we simply seek solution of this form. y2 equals vt times y1 for some function vt. And the goal is to find constraints for this vt, and eventually we can find this vt, and therefore we can obtain y2. Okay, and this is the only thing we will use for this method. We will not do Wronskian or Abel theorem, just very basic. Okay, so let's compute the derivatives. So y2 is v times y1, and then y2 prime is v prime y1 plus v y1 prime. And then y2 double prime, you apply product rule on both, and you get v double prime y1, and then you pick up this term from in each, and you get 2 of them, v prime y1 prime, and then you get v y1 double prime. Okay, and let's put all this back into the differential equation, which is 2t squared y double prime plus 3t y prime minus y equals 0. Okay, so you see I put it in y2 here, y2 prime here, and y2 double prime here. Okay, so we can now collect like terms of v. So we'll collect terms of v, v prime, and v double prime. Okay, so let's look at v double prime. It occurs only here, so we get this 2t squared y1. And now let's look at the term concerning v prime, which is 1 term here and 1 term here. And I can collect the coefficients, so I get 4t squared y1 prime, and then here I get 3t y1. And then let's collect the term involving the v here. If I take the v, then I get 2t squared y1 double prime. Okay, so y1 double prime, and then I have 3t y1 prime. I take out the v. Okay, and then the last one comes from here. I get y1. So the interesting part here is what I underlined here in red. What do you think that term is? You recognize that this is exactly the differential equation where you put the y to be y1. So what should this value be? Since y is a solution of this equation, therefore this would equal to 0. Right? So that term will be gone. Okay, so here we repeat it again. Since y1 is a solution, then this part, the red part, is 0. Okay, now we can drop this term, and then the equation becomes the first two terms add up to be 0. So I would like to comment that the fact that this last term becomes 0 might seem incidental, like maybe it just only applies to this equation, but let me assure you that which is not the case. So no matter what is your equation, if you seek a second solution in this form where y1 is the solution, then you will always get this term here with y1 and plugged into the differential equation. So this will always be 0. So why is that a fact? May I leave that for you as something you ponder and try to figure it out? Okay, now we got rid of one term, and then we just have two terms. So the function v here must satisfy this equation. So on the surface, this still looks like a second order linear differential equation, but we have only two terms, v double prime, v prime, and the term with v is not present, and that is very important. And that is exactly the key point that allow us to reduce the order to get this method, reduction of order. Now let me explain why that can happen. Okay, so now we can call v prime, call it a function, let's call it w. Then v double prime is w prime. Then we can rewrite this thinking now w is the unknown. Then I get w prime times the coefficient plus w times the coefficient equals 0. Okay, so y1 is already given. It's the first solution. So this is a function we know, and this is a function we know. And we see that treating the y here as the unknown, we now have a first order linear equation, which we know how to solve. Okay, here we see we reduced the order by 1. We started with a second order equation with one solution given, and then we end up with finding a function which is only a first order equation. The order is reduced by 1. Okay, let's look into the details to solve this. So let's plug in the function y1, which is t to the negative 1, and y1 prime is negative t to the power negative 2. We put that in, and terms will cancel. What would you get? Will be 2t double prime minus w equal 0. Okay, here because y1 and t, they cancel, becomes 1, and t squared y1 prime, they cancel, becomes negative 1. So you get negative 4 plus 3, which is negative 1. Okay, so this is a very simple first order linear equation. We know how to solve, so don't fuss over that, and let's see. We solve it and we get this solution. W is 3 over 2 square root of t. Yeah, but actually the w is not what we are after. We want to find the function v. So we can recover the v once the w is given. So w is v prime, and then v is the integral of w. We can just integrate the w to get the v. And then w is just a polynomial function. If you put it in, you integrate, it's just another power function. So it's t to the power 3 over 2. Okay, so now we can put this v back in. y2 would be v times y1, and this is the v here, and y1 is t to the negative 1, which give you t to the half, which is square root of t. Okay, so we're not surprised that we got the same function of y2. Okay, before we proceed, let's put put a couple remarks on method 2 or method 1 and method 2. So first remark is that we notice through the computation that this method is more complicated in the details of the computation than the first method, which uses Abel's theorem. However, method 2 is more general, although we did not show its application in other more general settings. So in the case that we do not have something like the Abel theorem, let's say you have a third order equation and you have one solution already given, then you can apply a similar procedure and then reduce the order, and you will end up essentially in solving a second order equation. Okay, so it's general. So you don't need to have something powerful like Abel's theorem. Okay. A second remark, I would like to catch your attention of this method and its similarity to something we studied maybe in high school. That is the situation in finding roots in polynomial. Let's say I have a polynomial, Pn, n is its order. So polynomial of degree n, so meaning the highest power term is t to the power n. Okay. Now if by some lucky guess or some bird whispered it to me that I find a root R1, then we know that this polynomial would contain the factor t minus R1. And then we know that Pn would equal to this factor, t minus R1 times q of t. And here the q of t would be a polynomial of degree 1 less, n minus 1. Okay, so remember we did a similar thing here to find the second solution. We say this is v and y1, and we multiply by a function v where we try to find, and we find out that in that procedure we can reduce the order of the differential equation by 1. Okay, so it's similar here, but okay, just a remark. Okay, so let's look at the third method. I'm sure some of the viewers here are wondering, well, is it possible to combine these two? So let's try to do that. So in this method, we will use Abel's theorem, and we use the wisdom from method 2, that is, we now seek a solution of this form, y2 equals v times y1. Okay, and hopefully with the combined wisdom, we would come into a even better method. Let's see. Okay, so first step, we apply Abel's theorem, and we find out that the Wronskian, it equals that. And this is worked out in method 1, so I just copy. And then in reality, you work this out. That is t to the power negative 3 over 2. Now, we seek the second solution, y2, to be v times y1. Okay, and then we use the definition of the Wronskian, w equal to y1, y2 prime minus y1 prime, y2. But then here we use this y2 simply equal v times y1. Okay, so, and that's y2, and that's y2. And then we differentiate this by the product rule. So I get y1 times the derivative, so differentiate v and differentiate y1 and then add them up. And then here we see that this term here actually exactly matches this term. This v y1 prime times y1 cancels that. So that's gone. So we have just one term, which is v prime times y1 squared. Note that this is a general derivation, and it does not depend on any specific form of y1 and y2, as long as y2 equals v times y1, the Wronskian takes this form. Okay, so let's put this in red, and since it's a formula, so we have this thing here. Okay, and this is a very convenient formula once it's derived, and then we can use it. Okay, so we know now y1 is 1 over t, and I can put that in. That's 1 over t, and then the Wronskian is v prime times 1 over t squared, and that shall equal to this number here, which we computed from the Abel theorem. So we immediately get an equation for v prime. Okay, and moving the t squared term over, we get v prime is t to the half, and then we can obtain v by just integrating that, which gives me this function. Okay, these are details that you know, I don't repeat. Okay, so again, we can just drop this constant. It doesn't matter. You can carry with you also. It doesn't matter. And then y2 is v times y1. Let's put it in the v times y1. And then this 1 over t is t to the negative 1. I'll just get t to the half, which is square root of t. Okay, so we see that method 3, after we have derived this formula, if we can use that immediately, the method 3 seems to be the one that is most efficient. Okay, so since this is the best method we discovered among the 3 of them that we studied, and from now on we will focus on using this method. Okay, and let's give a summary. So what is method 3? Okay, so the problem is, given a solution y1 to a differential equation, the second order linear homogeneous one, and we want to find the second solution y2. What do we do? So first, we find the Wronskian by Abel's theorem. So there is an integral to be worked out here. And then you can drop the constant into some number that makes this look simple. Okay, then we can solve the equation for v here by integrating, because now we know v prime is w times y1 to the power negative 2, which is now a function of t. We just integrated and we find this v. And again, you can choose a convenient constant. Any constant is okay. And then we can form the second solution, y2 is v times y1. And that's it, very simple. Okay. Okay, so I used an example and went through 3 methods in this video to come to this kind of a optimal method for this setting of our interest here. And I will end the video here, and next time we will take some examples of using Abel's theorem and using method 3. Okay, I hope you enjoyed this one, and I look forward to seeing you next time.